So last time we started talking about the families of the periodic table. We talked about the first three. So if you follow my mouse cursor, group 1, lithium through francium, excluding hydrogen, those are the alkali metals. Group 2 are the alkaline earth metals. And then groups 3 through 12, this rectangular spot, are the transition elements, or you can call them the transition metals. We're going to move on to this highlighted family today. This is a Mod Podge of a family. So this family is called the main group elements, groups 13 through 16. This family includes metals, nonmetals, and metalloids. So we're just going to say that the properties of these elements vary because it depends on what type of element they are as to their properties. These elements are either going to be solids or gases at room temperature. The metalloids and the metals are going to be the solids, and the nonmetals in this family will be mostly gaseous at room temperature. The stepped line separates these, so it's not visible, but I think I can draw it in. So the stepped line goes like this. Whoops, it's not that thick, but it goes like that. Okay, so that cuts this family in half. So to the right up here of the stepped line are our nonmetals. To the left of the stepped line are our metals. And then touching the stepped line on two sides are our metalloids. So as I said, you have every single type of element present in this family, and they are gases and solids. So some examples of elements in this family: boron. Boron is a metalloid, and it is used in heat-resistant glass. So it's added to glassware that we use in the lab or casserole dishes that can make glass be able to be heated to a very high temperature without breaking. Carbon, which is a nonmetal, has many different uses. So carbon is mined from the ground and its pure form is charcoal or coal. The graphite in pencils, although we say pencil lead, it's actually carbon-based. And then diamonds are made from pressurizing carbon at an extreme pressure and heat underneath the earth. Lead is a metal. Lead is very, very heavy. So if you've ever gone to the doctor or dentist and they put this vest over top of you, it's very heavy because it's full of lead. Now, lead at one time was used more efficiently in everyday life, and lead does cause poisoning. So when you have this vest on you, you're protected because it's not touching your skin, the lead itself. So lead stops x-rays from going through your body. So that's why they put this vest on you, and they want the x-ray to only go to the part of your body they're x-raying. The x-rays will not be able to penetrate through this lead suit, and therefore it's protecting your soft organs. But lead is toxic, so if you have an old house, they may have had to repaint because of lead paint. China, unfortunately, still uses lead in their paint, so sometimes you hear about toys being recalled from China because they paint with it, the lead paint, and then little kids chew on it and they get lead poisoning from ingesting that paint. And then phosphorus is a nonmetal. Phosphorus is found in matches. It helps that ignition. It's also found in gunpowder and things like that. And it also gives matches a little bit of that unique scent along with sulfur. So like I said, within this family, you have a lot of different types of elements happening: metals, nonmetals, and metalloids. Therefore, they're used in all kinds of things. So this is like the dysfunctional family of the periodic table. Next, we have the halogens. You can see them highlighted up here. This is group 17, fluorine, chlorine, bromine, iodine, and astatine or astatine. So group 17. The halogens are the most reactive non-metals. So we said that group 1, the alkali metals, are the most reactive metals. The halogens in group 17 are the most reactive non-metals. And when you combined a halogen with a group 1 or a group 2 element, you get what we call a salt. So this is supposed to be a little bit of a pun. It's Na, which is a group 1 metal, and Cl, which is a halogen, and they combine to form table salt, which is just one type of salt. So a halogen plus a group 1 or 2 metal produces a salt. So we said that the main group family had all types of elements, metals, nonmetals, and metalloids. The halogens are all nonmetals, but within this little family, you have all states of matter. So you have gases, liquids, and solids. So fluorine and chlorine are gases at room temperature. Iodine and acetylene are solids at room temperature. And remember, bromine is our other liquid on the periodic table. It's our non-metal liquid. So these are all non-metals, but all states of matter, solid, liquid, and gases. So halogens are mostly used in disinfectants. So the examples I give are mostly used in some type of disinfectant. So chlorine is used in bleach. Bleach is a disinfectant. You put it on your clothing to get rid of bacteria and germs. We clean with it. Clorox came from the word chlorine. Fluorine is found in toothpaste. So when you were younger, maybe you got a fluoride pill, or maybe your water is treated with fluoride. That comes from fluorine. Fluoride helps to protect your teeth and to prevent cavities. Bromine, as I talked about before, is a hot tub disinfectant. So chlorine is used in a pool, which is usually cooler temperatures. Bromine is able to fight bacteria at a high temperature. So you add this to hot tubs, chlorine would break down easier. And then iodine is used for medical disinfectants. So if you've ever had surgery or given blood, they wipe this brownish, orangish liquid on you. That's a disinfectant for your skin. So in general, halogens are used in disinfectants. And then our last main family are the noble gases, not Nobel, noble, like royalty. This is group 18 at the very end: helium, neon, argon, krypton, xenon, and radon. The noble gases are non-reactive. They do not react. They used to be called the inert gases, inert meaning unreactive. So I like to say these are the hippies of the periodic table. They are not going to react. They don't need to. And you'll learn why next chapter. The noble gases were discovered about the same time of each other, 1894, by John Strutt and William Ramsay. They were hard to find because they are gases, and a lot of them are lightweight, but they did discover them, and once they discovered one, they were able to discover many. So noble gases are oftentimes used in lighting. They have other uses, but they're found in lighting. Helium, as you know, is found in balloons. Helium is lighter than air, so that's why helium balloons can float. Helium is also very important to the medical industry and MRI machines. And I think I have a quick video. I'm going to try to show it to you. Okay, let me see if this works.
Hey guys, guess what gas we're talking about today? And the news is dire. This is serious stuff, people.
Despite the fact that helium is the second most abundant element in the universe, we're running out. Basically, helium is very useful for us because it doesn't really do anything. It's totally inert. It doesn't explode like hydrogen. It doesn't corrode like oxygen. That makes it perfect and perfectly safe for all kinds of crazy uses like making liquid crystal television displays and pressurizing NASA's rockets. Helium is also really good at making stuff like friggin' cold. It's used in the magnets at the Large Hadron Collider, which we talked about in a previous episode of SciShow, and in the MRI machines that doctors use to scan our bodies to figure out what diseases that we have. 25% of the helium that we use in the United States is used in MRI machines. And how, you ask, can we get more helium before we run out? Well, the answer is we can't. Really, unfortunately. So helium, second most abundant element in the universe. Care to take a guess at the percentage of it in our atmosphere? Hold that number in your head. Was it 0.0004 0.53%. That's 5 atoms of helium for every million atoms of atmosphere. Helium is produced by the slow decay of radioactive materials in the Earth's crust. And when it reaches the surface, because it's lighter than air, it just floats up right out of the atmosphere. But some of it gets trapped underground and is captured along with natural gas. The stuff that inflates your Mylar Feliz Cumpleaños balloon or whatever is extracted from those gas deposits. But not a lot of deposits have enough helium to make it worth extracting. That is probably why the United States government has a strategic helium reserve, which I didn't believe either when I first heard it, but we do. 16 billion cubic feet of this stuff trapped in dolomite deposits in Texas. And it's good that we have it because the United States of America eats up about half of the world's supply of helium. The government has actually been selling off our stash, about 2.1 billion cubic feet per year, to private industry. At that rate, we will run out by 2020. And it's not just regular helium that's running out, we're also running out of an isotope called helium-3. Helium-3 is only produced when the tritium in a nuclear bomb decays. And since we're decommissioning more and more nuclear bombs, we're running out of helium-3. Now, it turns out that helium-3 is really good at detecting radiation coming off of potentially dangerous nuclear materials, and so we basically bought the whole bar. Like, we have all of the helium-3 that exists, and we're using it to detect for nuclear weapons coming in at ports and airports and stuff. But since we aren't making nuclear bombs anymore, which I am totally in favor of, we're running out of helium-3. So what are we gonna do? Well, it's a good thing that 17-year-old Taylor Wilson just invented a bomb detector that doesn't use helium-3 and actually costs like 5,000 times less money than a helium-3 detector. This resulted in Taylor winning a $50,000 science fair prize and getting a patent that's probably worth significantly more than that. Speaking of that, we should probably actually just film a whole episode on that guy. He's pretty cool. So maybe there are some solutions for our helium-related problems, but some applications are just going to require a noble gas that's lighter than air, and there's only one of those. So either gas companies are gonna have to do some more extracting, or we're gonna have to get Lando Calrissian to build us a cloud city on Jupiter or something and suck up all the helium that Jupiter's got because it's not using it. But knowing Lando, he'd probably just lose the whole thing in a card game anyway. So what's the use? I shouldn't be wasting this, but...
Until next time, you can follow us on Twitter and on Facebook, and we're all...
So we're not officially out of helium yet, but we're definitely running low. And unfortunately, later in your life, balloons may not be something you can just get at the dollar store. They may be a luxury because it's more important to have helium for MRI machines and things like that. If you've noticed lately, if you go to like a party store or a dollar store, sometimes they have a sign on the door saying that they're out of helium. This is why. And helium is the only naturally occurring element lighter than air. So if we need something to float, helium is the only thing unless we come up with something new. Neon is used in lights. So neon lights, these are glass tubes, a true neon light, and they put different types of gases in here, including neon, and when you run an electrical current through them, they light up a different color. So if you break a neon light, you break the tube, it's pretty much useless because the gases escape and then there's nothing in there to light up. Argon is also used in lights. Krypton is used in fluorescent lighting, like the lights in the school, the long tubes. They're a little bit more expensive. And then xenon is used in tanning beds. Xenon is harmful to your skin. It mimics the sun's radiation. And then radon is extremely hazardous. So those are the noble gases. So once again, we covered the main group elements, the halogens, and the noble gases. I forgot I have one more funny video for you. This is someone that has a bunch of the noble gases in balloons. He's sitting on top of the building and he's going to show you which one's heavier than air and which one's lighter than air. So it's a little bit goofy, but it's a cool video.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
So you can see that the first couple, helium, obviously lighter than air, it floats with ease. Neon is just about as light as air, so it floats a little bit. The wind kind of took it, but eventually it will fall. The other ones were heavier than air, so they don't float, they drop. And the last one was so heavy you could actually hear it hit the ground. So there will be one more video finalizing the last two families of our periodic table, and then that will be it for chapter 5.